Now let's take a look at this stabilizer which is not working. We have the power coming in through this cord and power going out through this plug and an overload reset switch. Now firstly, let's check the resistance of the input. This is to confirm if there is a short circuit or not. So we see the resistance is in mega ohms. So this is not shorted and we can try plugging it in the main supply. Now I have plugged it in and we can see there is no light coming up in the front. Now let's try opening the cover. We can see we have 2 screws on this side and 2 on this side. By removing these, the top part will come apart. Now let's check the wire if it is alright or not. I will put the multimeter in continuity mode and check each strand of the wire if they are conducting or not. Firstly, let's try the earth. We have continuity. Now for the phase wire. This is the red wire coming in. And here we have the phase wire which is coming in. And we have continuity, but it is not in the right place where it should be. It should be connected to this overload switch. While we are at it, let's check the neutral wire too. This is the black wire coming here. And again, it has continuity. So this incoming cable is alright. But since we have found the problem that the phase is not even connected to the switch, this is due to the wire being pulled out. Now let's connect it back to where it should be. And this is pretty loose. That is part of the reason why it came off so easily. So let's tighten it down so that it fits more securely. I will bring some pliers for this. Here we have the needle nose plier. And I will just press this gently. Just a bit so that it makes good connection. Now you can see it is much more secure. Now for the original problem, the wire being pulled out, we should add some strain relief so that the wire doesn't get pulled again. But before that, let's try plugging it in and see if it is still working. So once again, I'll check the resistance. We have 27 ohms, which is fine, and that is due to the transformer winding. So now I'll try to plug it in. Now I'll turn it on. On the top right hand side, we can see the red LED is turning on now. So this was indeed the problem. So now let's fix the strain on the wire and close it back. To remove the strain, we can simply use a zip tie and tie it around on the inside of the wire so that it has some resistance when being pulled out. And now we can see even after pulling, the wire is not coming out easily. So now I will just put back the cover and close it. Here we have a small inverter which can be used to power small appliances like CFLs or LED bulbs. We have three outputs on the back which provides 220 volts AC, and the battery is inbuilt itself in the unit. So let's try removing the back cover and taking out the battery. Here we have a lead acid battery. Now let's measure the voltage of the battery. So we can see it is at 10.85 volts, which is a good sign because this means that the inverter is not shorted. So now instead of this battery, let's try powering it with the variable bench supply. So I will connect it now. Now let's decrease the current limit to, let's say, half an ampere. And now when I turn it on, we can see it is drawing a little bit of current. So let me flip this around so that we can see the indication LEDs. And also the inverter on LED is turning on. So now let's try connecting a small load to it. And when I connect the load, it immediately goes into battery low mode because we are getting current limited. So now I have increased the current limit to 3 amperes. And now we can see the load is drawing a little bit of power, around 9 watts. So the inverter section is working. So now let's bring back the battery, which I have charged using an external charger. Turn off the button before connecting it. Now if I turn on the button, the inverter is working. Now let's try connecting the mains cable into a socket. So now I will switch it on. Even after turning it on, we can see the mains on LED is not running. So there is an issue in the cable itself or the charging circuitry of the inverter. So firstly, let's try checking if the cable is alright or not. So here inside we can see the cable is coming in right here. And one part is directly going into the board and the other is going through a fuse. So let's check this fuse. Here we can see the fuse is blown. And it has blown gently. So now let's take a look at the ratings of the fuse. It is fast blow, 240 volts, 3 amperes fuse. So let's find an appropriate fuse for it. I will use a fuse with a much lower value. This is 240 volts, half ampere fuse, just to check if there is any other short or not. So now what will happen is, if there is a short which is still in the circuit, this fuse will blow pretty quickly. So now let's check the resistance of the circuit and check if it is shorted or not before connecting it to mains. So here we have around 6 mega ohms. So it is alright to plug it. Before plugging it in, let's connect the battery once again. Now I will turn it on. Now we can see the mains light is turned on. So the fault was definitely in the fuse itself. Now let's check if the circuit is even charging the battery or not. While the battery is still in the inverter circuit, let's probe it with the multimeter. So right now the battery is at 11 volts. Now if I plug it in, we can see it is going up to 13.4 volts. So the charger inside this inverter circuit is definitely working. So we have repaired this. The fault was in the fuse. Now I will put it back together. Here we have Arduino Mega board, which is not working. Even if we connect it directly to a USB, it is not booting up, or even if we connect the barrel jack, then also it is not working. So I'll bring a barrel jack connector which has two wires on the other end so that we can connect it to the variable lap supply. Now let's set the voltage to around 9 volts and let's set the current limit to a lower value. So firstly, this will go through this voltage regulator. So now when I turn on the power supply, we can see we have immediately went into the constant current mode. Now let's use isopropyl alcohol to find the shorted component. I have this in this spray bottle, which is convenient to use. Now let's increase the current to 0.2 amperes. And we can see again it is in the constant current mode. So the shorted component will get heated up. And this isopropyl alcohol will tell us which component is heating. This is a quick and easy way to find an overheating component. So let's find the component on which the alcohol vaporizes quickly. Let's increase the current so that the alcohol vaporizes much more quickly. I will increase it to half an amp. I think we have found our component. You can see it is vaporizing so quickly, and it is also hot to touch. So we have found a component which is probably shorted. So now let's turn off the supply and desolder and remove it. So I will bring my hot air gun for this. Now let's check for short in this voltage regulator. So we can see that this voltage regulator is definitely shorted. So let's bring a new one. Here I have a packet of voltage regulators. So now let's solder this new one in the old one's place. Now let's try to power it with the same setup that we used before. Now we can see the light is turning on. Let's increase it to 0.2 amperes. And now we can see the Arduino is booting up. The standby light is turning on. And if I reset, we can see the light on the left, it is lighting up. So now we have fixed the Arduino. So here we have a battery charger which is used to charge lead acid batteries. And currently we have no output from it. So let's try to open it. It has 2 screws on the top and 2 on either side. Here we have the first look inside the charger, and we can see it is a relatively simple design. It has a transformer which steps down the high voltage AC, and we have a bridge rectifier made up of 4 discrete diodes. So firstly, let's check if the input wire is alright or not. So the wire comes here, and the 2 ends are these black and the red cable. The black one goes to a fuse, and before checking anything else, let's check the fuse. The fuse looks alright. Let's confirm with a multimeter to be sure. And the fuse is alright. So let's put it back in its place. Now back to checking the input cable. I will place one probe of the multimeter on one end of the plug and check the other end. So in the red wire we have continuity. Let's check the other one. So here also we have the continuity. Now let's check the resistance between the 2 wires. It is around 230 ohms. So now this control knob on the front, this is used to switch between the different windings on the transformer. So in the setting number 2 we have 10 ohms, in 3 we have open circuit, in 4 it is around 8 ohms, and in 1 it is around 2.9 kilo ohms. So this knob seems suspicious. These are the secondary windings of the transformer. And after the rectification, it goes through the ammeter and into the binding post on the front. Let's confirm if the windings of the transformers are alright or not. The selector switch wires come into these connectors right here, which are on the transformer. So these are basically different taps on the transformer. So by putting the multimeter in ohms mode, let's check the resistance. Let me adjust the multimeter a bit. Now here we have around 7.6 ohms, 9.1 ohms, 9 around 10.6 ohms, and we can see the windings of the transformers are alright. So the knob at the front is definitely suspicious. Now let's remove the knob from its place. These two screws will remove it from the position, and it is free now. Let's check the resistance between the knobs. So the center point is connected to the other four depending on the position of the switch. So we can see the resistor is jumping around. So the contacts between these are worn out. Now to test the transformer, what we can do, we can connect the whole winding of the primary side to the mains input. So we will be using the black and the white inputs, which is basically the whole winding. And the other ones are the taps between the black and the white. Now let's check the resistance. So this is between the full winding, and it is around 11.3 ohms. While we are at it, let's also check the diodes. So I'll put my multimeter in the diode test and check all 4 of them individually. Place the negative probe on the cathode and the positive on the anode. And you should see a voltage drop. So this is having a loose contact somewhere. If you get a loose contact, you can rub the leads of the multimeter on the pin. So the diodes are fine. Now what we can do, we can have a bulb in series to be connected. So what it will do, it will keep the current limited if there is a short. And we can try running it on the main supply. So I will be using this 100-watt bulb. So this will limit the power to 100 watts. And I will place this bulb in series with the load. Let's tape the wires for some insulation. So basically the whole primary winding is in series with a 100-watt bulb. Now I will place the multimeter in the outputs to check if there is some voltage. Now when I turn it on, we can see there is some voltage present. We have 11, 10.8 volts. So the transformer is working. Now let's try attaching some load to it. I will be using this bulb. This is a 12 volts bulb from a car headlight. So we can see the ammeter is also working. So now the only thing we need is to replace the selector switch on the front. So let's see how it works. I will pry this open with a screwdriver so that we can see the internals. When it comes apart, we can see there is a central contact and a moving slider contact which connects the center portion to the remaining 4. And we can see there is some corrosion here. So that was the reason why it is not working. Now let's draw a basic schematic of the circuit so that we can understand more clearly how this circuit works. So this is a very simple circuit. and we can draw this on a sheet of paper. So we have the AC incoming from the cord, and it goes through a fuse. And after that, we have a switch. And one wire of the AC input is directly connected to one side of the transformer's winding. And the different taps are arranged like this. And the colors of the wires are here. And then on the secondary side, we have a bridge rectifier. Now, a simple way to remember which side is the positive and the negative is that when the diode seems to go away from a point, so that is our negative part. And when the diode seems to come together to a point, that is our positive part. The negative side directly goes into the binding post, and the positive goes through an ammeter. So the construction is as simple as that. And regarding the selector switch on the front, that switches between the different windings of the transformer. We have one AC line incoming to the center, and depending on the position of the switch, it is switched between the blue, green, yellow, and the white wire. So by switching between the different tappings of the winding, we can increase or decrease the output voltage. So now while we are at it, let's also look at the inductance of the windings. So between the full winding, we have 10.7 ohms and 18 henries of inductance. Now I will switch to the yellow winding, and we can see the resistance and the inductance have decreased because a part of the winding is not in the circuit now. Now the green wire, the resistance and inductance is even lowered. And now the shortest possible winding in this configuration. It is 7.7 ohms and 12.1 Henry. And again, the full winding. So now we just need to replace the selector switch on the front and close the box. And it is working again. So here our issue was the mechanical contacts in the front selector switch. Here we have a lab bench supply whose output voltage keeps fluctuating. Let's take a look. When I turn this on, take a look at the two channels, the voltages of the two channels. They keep fluctuating without even turning the voltage knob. You can also hear the relays clicking. So let's open this up and take a look inside. We have screws on both sides as well as on the top. Now after taking off the top cover, we have a first look inside the bench power supply. So we can see we have two separate transformers for two separate channels and rectifier boards for each of them. And the control board and the display board is common for both of them. Here are the primary smoothing capacitors. And here are the relays that we heard clicking. Let's check if there is any voltage present on these capacitors. I will carefully probe them. And they only have half a volt. So we can proceed. This capacitor right here, we cannot measure the voltage from it. But once we have removed these two bars on either side, then we will be able to access that capacitor also. So the front panel is held on by two screws on either side and one in the center. So let's remove them. The primary suspect here are the potentiometers on the knobs. So we are trying to take out the potentiometers. So this top board has the 7-segment LEDs built in for the display, and beneath that board we have the potentiometers connected. So we have to remove that too. Now the board is held in place by these potentiometers, and each of them has a nut. So let's remove those nuts. So now after removing all four of them, the board comes out. Let's check the resistance of these potentiometers. Now let's check the resistance of this first one. we have around 20 kilo ohms, and it jumps all over the place when I turn the potentiometer. The next one is almost stable. It is around 6 kilo ohms, but the maximum it can be is 5 kilo ohms. And the fourth one also seems alright. Now let's remove them from the circuit and test them again. Now we have removed the first potentiometer. Now let's again check the resistance. So we can see without even turning the knob, the resistance is jumping around. And the total resistance is 5.8 kilo ohms. Let's check once again. It's 13 now. 4. And just by touching the knob, we can see the resistance is jumping. So this potentiometer has a bad contact on the wiper. Let's take a new potentiometer and check how it should behave. Let's check this 47 kilo ohm potentiometer. And you can see the value is pretty stable. When I set it to 15, it stays at 15. So this potentiometer is faulty. Now let's remove the other ones too. This one is also a 5 kilo ohm potentiometer. And we can again see the value is jumping around. So let's remove the two also. Because if one potentiometer is faulty and the others are also of the same make, so they may be faulty too. So if we are replacing them, it's a good bet to replace all 4 of them. This one is also faulty. Now only one remains. This one is also faulty. So all four of them are faulty. So let's replace them with new potentiometers. This is a new one, and we can see the resistance is pretty stable. Now when two of them are changed, let's try to run it, because only two potentiometers are required for one channel. So I will cover up the display with some plastic so that there are no short circuits, and I will carefully power it. Now we can see the voltages are pretty stable. Earlier, as we saw, they were jumping around. So I think the problem has been solved. There was loose contact in the potentiometers, and that was causing the voltage to jump around. Let's try attaching a load. Now we can see the other potentiometer is working too. So I will now turn this off and discharge the capacitors once again, and then we can proceed to solder two other potentiometers on the remaining two slots. Now we just need to close this back in the reverse order as we have opened it. So firstly, we will place the potentiometers in the right location, and then screw the bottom board, and then after that we will screw the display board. Now let's test this power supply once again to make sure it is working. Now we can see the voltages are stable and are not jumping. Now let's connect the load. So now the power supply is fixed. Now we have stable voltages and current values. So the problem was just in the potentiometer knobs. The wiper contact has aged and caused it to jump in resistance value. So here we have a UPS which is not working. So the first thing naturally is to check the fuse. And the fuse is intact. So now let's try to open it. We have 4 screws at the bottom. So I will remove those. So now the top cover comes off. And firstly, let's disconnect the battery. And now taking the first look, I do not see any burnt components. So now let's measure the voltage of the battery because that is the first thing to give up. We can see the battery is at 6.5 volts, which is considered dead. So because the battery is dead, we can try powering it with a lab bench supply to see if the circuit is still working or not. Now here we have the lab bench supply. I will connect the negative to the negative and the positive to the positive. Now I'll set the voltage to 13.6, which is of a fully charged lead acid battery, and the current will be limited to half an amp. So now when we try to turn it on, we can see it is beeping and trying to turn on, but is shutting down. Let's try that one more time. So maybe the issue is with the current. So let's increase the current limit a bit. Two amperes will be fine. So now the UPS is turning on properly and is drawing around 8.5 watts of power. So let's try to measure the output voltage. I have set my multimeter to AC voltage. And now I will carefully probe the outputs. And we can see we have 236 volts on the output. So the inverter is running. So the problem here was probably a dead battery. So I have replaced the battery with a new one and I will carefully close it up. And these connections seem a bit loose, so I will tighten them. These connections need to be tight enough because lots of current will be flowing through these. So now you can see these are secure. So now careful not to pinch the wires together. And when it is done, now I'll screw it back together. And now let's test it. So I'll connect this UPS to this mains outlet and I will attach a load to it. This is a simple 20-watt LED bulb. So now when I turn on the AC supply and also turn on the UPS, we can see the LED bulb lights up. And even after I disconnect the AC power, the UPS doesn't stop the power going to the LED bulb. So this UPS is fixed. The only issue here was the dead battery. We have a desktop UPS here which is not working. Now to open it, we have 4 screws at the bottom. So now we will need a longer screwdriver to open it. Now we need to find the screw, then gently press it and then unwind it. Now after we have removed the screw, we need to take it out. For that we can use any magnet, just like this. Now we have the first look inside. We have the battery, the transformer and the PCB. Here is the battery. Now let's check the voltage of the battery. So it is around 10.7 volts. So the battery is not dead, just discharged. Now let's power it using our variable supply. So now we have the current limit set to half an amp. Now when we power it, the circuit tries to boot but doesn't start up. And I do not hear any relays clicking. Now let's remove this PCB. We have plastic snaps on either side which are holding the PCB down. So we can just flex the case and remove it. These were the retainers that were holding the PCB down. These are just push to clip. Now let's clean the PCB a little bit. These connectors are not coming off easily. So let's remove the other ones, the transformer and the incoming mains cable. So on the first visual inspection, I do not see any burnt components. Everything seems intact. We have the power coming in here. And these are the switching MOSFETs. So because we did not hear any relays clicking, so those are the first suspect. Now let's check the incoming cable. These cables are terminated onto these connectors here. And the output goes through this transformer. And these are the different taps on the windings of the transformer. So the output of this UPS is being controlled via those relays and through this transformer to the outputs on the back. So since we are having no output, then we should check the relays. I will again bring my bench supply for this. Now these relays, they run at 12 volts. So we will be needing 12 volts to actuate them. Now I will be using the probes on the multimeter and connect them to the output of the variable lab supply. And now let's set the voltage to 12 volts and the current to 0.1 amperes. Now we will have 12 volts on the tips of the probe. So now we can actuate all these relays one by one and check which are working and which are not. So these are the coil contacts. And here are the coil contacts for this one. We have in total 4 relays on the board. So let's test them one by one. Here it looks like a short circuit. Also, there's a short circuit in the opposite direction too. Let's test this one. Here the relay is turning on and it is taking 0.25 watts of energy. But this one here, this is a short circuit. Now for this one, this is also a short circuit. Again, the working relay, which is taking 0.25 watts. Now let's test the last one. This one is also turning on and this is also taking 0.25 watts. So we have 2 relays which are good and 2 relays which seem bad. So I will mark them now. These 2 were working and this are not working. These are the 2 which are not working. So let's try to desolder them from the board and check them again. Each relay has 5 contacts on the PCB. So now this relay is out. These two are the coil contacts, and this is the normally closed switch, and the other one is the normally open switch. Normally closed, normally open, and these are the coil. So let's check again if the relay is short or not. Again using the same values, 12 volts and 0.1 amperes. Now the relay is working. And we can see it is also drawing 0.25 watts. So the relay is alright. So the short is on some other component on the PCB. Let's check if there is still a short in the PCB by checking continuity around the coils of the relay. So we have a short circuit here. So there's definitely some component shorted here. Now to drive this relay, we have a small transistor here. And across the relay, we have this diode, which is used to prevent from the high voltage inductive spike. So let's check this diode too. And we see a 0 volt drop on this diode. So this diode is shorted. Also, let's check the other one to be sure. And this one is shorted too. This is the first diode. So let's remove these diodes from the PCB. The pins are bent on the PCB. So let's straighten them first. So again, we can see this diode is shorted. So since this is a diode used to prevent the inductive spike, so any diode can work in this place. So I will be using this diode. This is a general purpose diode. So we can see this is all right. So now let's remove this one too and replace both of them. So now the short is gone. Now let's solder the relay back. Now after this, I tried powering the PCB, but the relays are still not turning on. So the next suspect is this transistor. This transistor is used to drive the relays. So let's remove them from the circuit. Now the solder is melted and it is out. This is the transistor which was turning on and off the relay. So I do not have any small outline transistor like this. So I will be using a through-hole transistor. This is a general purpose 2222. So firstly, let's check if the transistor is alright or not. And this is alright. And the pins are emitter, base and collector. So now we need to match these pins to the pads on the PCB. Here we have a handy symbol which is showing the pinout of the surface mount part. So I will match them and I will botch this transistor on the pads of the PCB. This is just for testing only. If the circuit works by this, then I will order some small outline transistors, the SMD ones that we just removed, and replace them. So this is the correct pinout and I will use some flux. So the emitter and base are soldered, and the collector too. So now let's do the same for the other one too. Again, I will use the hot air gun. Now the same procedure will be done for this transistor too. It's a good practice to check if the parts are working or not before putting them in the circuit. So again, I will match the leads to the pads on the board. And we have soldered the transistors to temporarily check if the board is working or not. Now again, I will apply power. This time the current limit is increased to 2 amperes. So now the board is working. So I will assemble it back again. So here our issue was the transistors which were driving the relay and the diode which is used to prevent the high voltage spike. So after replacing that, the relay started working and the board is working fine once again. And we have fixed this. You will find switching power supplies in many kinds of machines. Today's AC adapters and battery chargers are also little switching supplies. We also have standalone switching supplies. Now, any switching supply works by rectifying the incoming AC into DC and then chopping it at high frequency. Using a high frequency allows the energy to be replenished on the other side of the transformer much more frequently compared to the old linear approach, which was limited to line frequency, which is 50 Hz or 60 Hz. Efficiency is improved by regulating the output voltage using pulse width modulation. Instead of making more power than it is needed and then throttling it back with a series pass transistor, pulse width going through the transformer is adjusted to let through only as much power as it is required to keep the output voltage constant. Now let's take a look at the parts of a switch mode power supply and how they work together. The first thing that we have is the incoming power supply, which goes through an EMI filter. EMI filter consists of this common mode choke, these capacitors, and after that we have the bridge rectifier. So let's draw a block diagram for it. Then after the EMI filter, we have the bridge rectifier. After the rectification, we have a NTC thermistor right here. This stands for negative thermal coefficient. This is basically a resistor which has a high resistance when it is cold, and when it heats up, the resistance goes down. After that, we have the main smoothing capacitors. Now this filtered DC goes into these transistors. These are the main chopper transistors. These transistors switch the DC into high frequency AC pulses. Now these pulses go into this main primary transformer. Now from this main transformer, we again have these double diodes. These are two diodes in the same package. So these are used to rectify this AC on the secondary side. So after the rectification, we need to smooth this. So for that, we have these inductors and these capacitors. So they act as the filter. And after that, we have our output. Now we also have this control IC. This IC controls the pulse width that is going into the bases of these transistors. So this basically acts as the control IC for these transistors. This IC monitors the output voltage and the output current and maintains the pulse width accordingly. So from the output, we have a feedback going into the control IC. We have the feedback right here. So this control IC, this generates the pulse width modulated signal which is required to drive these transistors. So it looks something like this. Here we have a dead time, which is the time in which neither of these transistors are turned on. We have the feedback in the form of the voltages provided by these shunts. Sometimes we also have an opto-isolator when this IC is on the primary side. But since in this case this IC is on the secondary side, so it can sense the current going through these shunts directly. And also the basis of these transistors is driven using this transformer. So we have isolation from the primary side via this transformer and via this main primary transformer. So let's take a look at how the pulses will look. So firstly we have the incoming AC, which will look like this. Then after that we have the rectification. So it changes into only positive sides. Now these capacitors will make this into a much more DC looking signal like this. Then the transistors, they will chop this signal into high frequency pulses. Now these pulses go through the transformer and this just steps it down to a smaller voltage. Now again we have the rectification. So after the rectification, the pulses will look like this. And then after the filtration, the pulses will again look like a DC signal. And this is our output. And we have the feedback to the control IC. And this control IC directly controls the transistors. So here we basically have two sides, the primary side which is connected to mains, and we have a secondary side which is isolated from the mains using this transformer. So the part here, this is our primary side. And this other side here, this is our secondary side. So we have isolation in between these two sides via this transformer. And we also have cuts in the PCB itself to isolate them even further. So this is the simplistic model of the working of SMPS. Also, one thing to note here is that this is a half bridge configuration. There are other configuration of switch mode power supplies too. But this is the basic idea of how a switch mode power supply works. Now let's see how to assess the repair. Unless the transformer is shorted or open, it is generally worth repairing a switching supply, especially if it is inside a product that you want to get working again. It might be a waste of effort on an AC adapter that could be replaced easily. If multiple semiconductors have blown from a chain reaction, feeding voltage from one stage to the next, fixing the supply may be more trouble than it is worth, especially if the control IC is dead and getting the part is a hassle. Now let's look at the risk involved in servicing a switch mode power supply. The first one is the shock hazard. Always disconnect the power first. Never work on one with power applied. Now, switching supplies are organized in two sides. A primary side connected to the AC line with no ground connection to the rest of the product circuitry, and the secondary side isolated from the AC line by the transformer and connected to circuit ground in the rest of the device. The primary side of SMPS is where the most of the trouble is, and also the most of the danger. The chopper circuit stresses the transistor harder than any component in the supply, leading to frequent failures. Now let's see how to repair an SMPS. Most SMPS fail from bad electrolytic capacitors, blown rectifiers, or a dead chopper transistor. Check the blue metal oxide varistor used for surge suppression at the AC input. If it is burned, the supply has taken a serious voltage spike, perhaps from a nearby lightning strike, and is likely to be badly damaged. Next thing to look at is the capacitors. Any bulges, you need to change them. Any leakage, change them. Anything at all unusual about their appearance, change them. If they look fine, check them with your ESR meter. Checking the rectifiers is easy enough, as if they are separate diodes. Now the next thing is the chopper transistor. It is probably connected to the heatsink on the primary side of the transformer. Some choppers are bipolar transistor, but most are power MOSFETs. Small supplies might use a chopper in an IC package. If the fuse is blown, it's a good bet that the chopper has shorted out. The transistor can fail open too, in which case the fuse might still be good. The transistor may have shorted and then opened, and the fuse may or may not have survived the momentary overcurrent. Check the transistor by removing it from the circuit. It is best not to scope the chopper or any component on the primary side directly. If you have an isolation transformer, then you can try connecting directly, but even then it is not recommended. The best way is to connect wires to the transformers, the gate driving transformer, the primary transformer, and the output inductors. You can add a single turn of wire to each of them and then look at the signals so that you will be isolated from the high voltages. Now, if the chopper is running, you will see pulses at a lower voltage than the other side. If there are no pulses, then the chopper transistors are not running. If the choppers are good, but they are not operating, then the suspect is the control IC. If the supply is running but not putting out proper power, capacitors on the secondary side are the primary suspect. Also, many switches will shut down if output current demands exceeds their safe limits. Some may blow their fuses for the same reason. A short somewhere else in the machine may be pulling too much current and causing the supply to act like it is broken, when it is really just protecting itself. Now let's visualize the current flowing through the different components on this switch mode power supply. This base driving transformer, this main transformer, and the output inductor. I have added a loop of wire around all three of them so that we can visualize the waveform. I will be using this portable oscilloscope. By adding these turns of wire, we are safe from the high voltages present on the PCB. I will be using these three bulbs as our load. These three bulbs are connected in parallel. So here we have three of the positive and three of the negative terminals. So I'll connect positive to any one of them and negative to any one of them. I will also connect my multimeter across the output so that we can see the voltage. Now let's turn this on. Now the supply is on. Firstly, let's probe the base driving transformer. So this will present us the signal that is going into the base of these transistors, the main switching transistors. So let me adjust the signal a bit so that we can see it better. So here we have the waveform which is going into the transistors. See the difference when I remove the load and reattach it. Whenever the load is attached, the basis is getting much more current. The upper half of the signal is for one transistor and the other half is for the other transistor. Notice how the voltage remains the same because the control IC is regulating the pulse width accordingly. Now I'll change the voltage. And as we increase the voltage, we can see the current going into the bases gets stronger. While there is no load attached, the transistors are only getting little bit of currents on the base. Now let's move to the main primary transformer. Now I will readjust the settings on the oscilloscope so that we can see the signal better. Now let's connect the load. Notice how the waveform changes as soon as we connect a load. So this is the waveform without load. And with load, it changes to this. Now let's move to the output inductor. Now with the load attached, we see some ripple. Now let's see what happens when we remove the load. The ripple gets smaller. So here we have a faulty switch mode power supply which is not working. This is a standalone version which outputs 5 volts and can deliver up to 40 amperes. So now to open it, we have these two screws holding the blue top cover. So let's unscrew them. The other screws here, these are for holding the transistors and the diodes to the heatsink. So now to remove the cover, we need to slide it above, like this. We have these contacts which slide together to lock it in place. Now without touching the PCB, you can remove the fan header. Now the first obvious hazard here is these capacitors. So we can see to remove the PCB from this housing, we need to remove these transistors from the heatsink. Now the PCB can slide out of its place. We have these capacitors here. So first let's check if they are charged or discharged. So they are discharged now. Now we have the first look on the PCB. And we can see that the fuse is melted. Now let's check the primary input stage with the multimeter. So we can see the fuse is open circuit. Now after the fuse, we need to check the bridge rectifier. We have this bridge rectifier here. This is in a single package. The 4 diodes are here. So here we have the positive and the negative and the 2 AC inputs. So we can also check them like a discrete diodes one by one. So we have half a volt drop here and half a volt in the other direction too. We again have half a volt, and for the fourth diode we also have half a volt, and in the reverse they are open circuit. So this bridge rectifier is alright. Next we have the NTC thermistor. So let's check the resistance of it. It is around 3.6 ohms when it is cold. It will drop when it gets hot. Now we have these capacitors. Let's check the capacitance. It is around 337 microfarads. And we have 470 microfarads written on them. Not in their prime, but they're alright. So here are the main switching transistors, D13009K. And here are the double diodes. These are 2 diodes in a single package. Since they have a common cathode, we need to place the negative probe at the center leg. So here we have 0.065 volts of drop, and on the other side we have 0.065. So these diodes are alright. The reason we are seeing such a low voltage drop is that they have a low voltage drop itself. Now the only thing remaining in the circuit are these transistors. So let's remove them from the PCB to check them. Now they are out. So this is shorted. And this one is also shorted. All 3 legs of these transistors are shorted together. And same for the other one too. So now let's check if the PCB is alright or not. We need to make sure the short is in just the transistors and not the PCB itself. So we do not have any shorts right here. And we can see this is the base driving transformer. The bases of these transistors are controlled via this transformer. and this transformer is also not shorted. So now let's check these diodes, which are used to prevent the transistors from high voltage spikes. So this is fine. Both of them are fine. Now to test if the PCB is working fine or not, I have these other transistors which have the same pin out and the same voltage rating. They can handle much less power than the original ones, but they will be enough to test if the circuit is working or not. So you can see these are also NPN transistors. The main important factor here is that they should be able to withstand the full voltage that the original ones did, which is 400 volts. So both of these are rated for 400 volts. The only difference is these can handle much less power. So since we are replacing them for a quick test, so we do not need the full power. Now I'll connect this lead. Now the one thing that we forgot is to replace the fuse. So let's do it now. So this is the blown fuse, and I will replace it with a similar one. So this is another fuse from another supply. I will use this plastic sheet to insulate it from the debris. So now I'll plug it into a current limited supply so that if there is a short, the current will be limited. So now we can see it is outputting 4.983 volts. So the circuit is working. Now that we have the confirmation that the circuit is working, so now we can arrange for the original transistors with the same part number. But first, let's discharge these capacitors. We can see we have around 8 volts. So I'll discharge them using a resistor. These transistors are not even warm. Now I have brought other transistors from a similar supply. These are the exact same part number. So firstly, before installing them in this board, let's check. So we can see these are also NPN with emitter collector base. So now I will remove these test transistors and replace them with the original part number. So when we are installing them, we need to make sure they align properly with the heatsink. Now since we have the new transistors, we need to reapply the thermal paste. So for that, let's remove the thermal paste from these diodes too, so that we can have a clean layer on all four of them. Now we need to clean the thermal paste of these insulating pads too. Also, I clean this insulating layer. Now we just need to apply thermal paste and install it. I have this heatsink compound right here. So firstly, I'll apply it to these insulators so that they stay in place. Now this thermal paste is way too much. You do not need to apply this much. Only a small drop will suffice. I will carefully align them and press them on the insulating pads. So now let's use the original mounting method. This piece of metal holds down both of these diodes and presses them to the heatsink. So now the installation is complete. Let's connect the fan and put on the top cover. Now let's turn it on. And we have 5 volts at the output. So this supply is fixed. The issue here was that the transistors were shorted and they made the fuse blow. So after replacing both the transistors and the fuse, the supply is working fine now. And I will adjust it to exactly 5 volts now. So here we have a desktop SMPS which is not working. I have taken the top cover off and now the PCB can be removed by removing these 4 screws. Now we need to discharge these capacitors. These are the pins. In this arrangement, we can see the voltage while we are discharging the capacitor. So this one is already discharged and the other one is already discharged too. Now I will clean the PCB a little bit. There's so much dust here. Now the PCB is clean and we can take a look. The bottom looks alright and there are no burn marks. Let's visually inspect the top portion of the PCB. So everything here seems alright. No burnt components or anything. Now let's test the connectivity from the connector plug to the PCB. We have continuity in one of them. In the other one too, we have continuity. Now the fuse is alright. Now let's check the diodes. This is good. This one is good too. Now for the other two, we need to change the polarity of the probes. So these two are also good. So all four of them are good. Now let's check the NTC thermistor. So it is 6.3 ohms. So that is fine. So our next suspect are these capacitors. So let's check them. And we can see the capacitance has dropped to only 56 microfarads. And it should be much greater than that. So let's remove them. So now the capacitor is out and we can see it should have been 330 microfarad, but instead it is only 56 microfarads. So I think we have found our culprit. So let's change these capacitors. So this one is around the same capacitance but has a higher voltage rating. So that is fine to replace. So now let's solder them in place. Just make sure you are setting them in the right polarity. Now let's check if the circuit is working after removing the capacitors and replacing them. So I will use this 100-watt bulb in series with this SMPS so that if there is a short, this bulb will limit the current. I will use this board to turn on the ATX supply because it needs a signal to turn on. And we can see it is turning on. And the bulb is not glowing. So that means the supply is not drawing any current right now. So now let's attach a load to it. Now when the supply has to power a load, it will draw some current from the mains. So now the bulb should glow. Now when I turn on the supply, you can see the supply is drawing some current. So the 100-watt bulb is glowing and also the smaller bulb is running. So now let's see that with the lights off. First, the current limiting bulbs light up because the supply is drawing some current. And when the capacitors are charged, it starts giving power to the load. Now let's see it in slow motion. So now we can say the supply is working. So now let's carefully turn the PCB around and discharge the capacitors. Now we can simply put the PCB back on its enclosure and now the supply is fixed. Here our issue was that the capacitor dropped in its capacity. Instead of being around 300 microfarads, it was around 50 microfarads. So that was the reason why the supply was not running. So this repair was simple as replacing those capacitors.